Hello and welcome back. Let's talk about the fundamentals of a program. Since this is a beginning programming class, specifically we're going to be talking about C. Before you can understand even a programming language, you need to understand what a program is. So I want to describe some basic concepts to you before we get started in the details of C. Computers are very dumb machines. You guys are, I'm sure, more than not familiar with what a computer can do and what it does. Specifically though, under the hood and what's going on in terms of when you click your browser, when you click your different applications that you use, what's happening under the hood is there is some kind of program that's running, and that program is telling the computer what to do. Computers are really dumb. They only do what they're told to. So the basic operations of a computer will form what is known as the computer's instruction set. Right, and an instruction set, if you can kind of think about that, it's just how it's going to do something. So we need to tell this computer how it's going to do. We do it in the form of a program. At an even lower level, each computer has what's called an instruction set. And an instruction set is basically the instructions on the CPU, the processor of the computer. So to solve a problem using a computer, by telling it what to do, you provide this solution by sending these instructions to the instruction set. So that's what's happening when you write a computer program, is you're sending specific instructions to solve a specific problem via commands to the CPU, the processor, okay? And the approach or method that is used to solve the problem is known as an algorithm. So for you guys that understand math, an algorithm is just, again, how you're solving a problem. So for example, if you were to create an entire program and all it does is test whether or not a user enters an odd or even number, what would be described as the algorithm itself is the test, whether or not the number is even or odd. That's the algorithm. The statements that solve the problem in its entirety becomes the program. And we'll discuss this concept in algorithm. Algorithm is even more kind of related to module programming. So we'll talk about that when we talk more about the details of C. But again, I want to let you understand what you're doing when you're writing code. What's going on at the very, very lowest layer. You're going to write these algorithms that are contained inside of a program. So to write a program, you're going to need to properly write the instructions to implement the algorithm. These instructions can be expressed in any kind of statements of a particular language, programming language. So we're going to focus on C for this class, but I'm sure you've heard of other programming languages like Java, C++, Objective-C is used in iOS applications, but actually more now, it's Swift is used. But there's all these different programming languages that you can learn that essentially are going to allow you to send instructions to the CPU in the form of algorithms and statements. Also, want to talk about some basic terminology. The CPU, the central processing unit. This is the brain of the computer. This is where most of the work is being done. This is where instructions are executed. Memory. You often hear this term memory, and students often get memory very confused with the hard drive. Memory is not the same as the hard drive, right? Memory is often referred to as RAM, which is random access memory. All of the data that's stored in memory, it's a separate hardware component. It's not an actual disk drive. All of the data in a program is stored in memory, this separate hardware component. So it stores the data of the program while it's running. And we're going to talk about variables and what they mean, but a program needs to have data in order to perform calculations, in order to do algorithms. That data is going to be stored in RAM, memory. The reason we store it in memory as opposed to storing it on a hard drive is that memory is much faster. It allows the program to run much quicker. But memory is also usually not persistent across reboots, another kind of clarification. But you should understand just this term RAM. It means memory. It's the variables and the data in the program itself where it's stored. It's a separate hardware component than the hard drive. The hardware drive is something you buy with the computer that's permanent storage. This is usually really, really large, contains gigabytes, terabytes of data. This stores files that may be resources of a program. And when you turn the computer off and turn it back on, those files are still there. When you turn the computer off and on, and the program actually stops executing and there's nothing in RAM. So understand the difference between RAM and hard drive. It's an important concept. Again, think of RAM as related to programs, hard drive related to permanent storage, and we usually put resources on there. We'll have operating system files, all sorts of different program resources. An operating system is developed to basically make your life a lot easier when you want to use the computer. Because at a very low level, a computer is just doing what it's told, and it's just instructions on using an instruction set, it would be very, very difficult to use if you were to have to understand all these instructions. So there's a program called an operating system that makes it easier for a user to use a computer. It controls all the operation of the computer, handles all the input and output via hardware, so it understands how to interact with a keyboard, a mouse, a monitor. It also manages the computer's resources, handles execution of different applications. An operating system is a completely separate class. There's a lot that goes into an operating system, but understand the basics of it. It's just allowing you to use your computer in an easier manner. Some examples of very common operating systems are things like Windows, right? Everybody uses Windows, Windows 10, Windows XP, whatever the case may be. Linux, Unix, which we'll talk more about when we talk about the history of C. Android is an operating system for mobile devices. iOS. These are specific programs that are very large that may contain many different programs that interact and make your life a lot easier with interacting with the computer. The FEX execution cycle. This is the life cycle of a CPU. I only mention this because, again, we're just describing basic terminology. This is how, when you send instructions to a computer, the CPU, what's actually happening is you're fetching the instructions from memory because that's the program, and then you're going to execute that on the CPU. And it's this kind of loop. You're doing it over and over and over. You're repeating it. And if you've ever heard of the term gigahertz, a gigahertz CPU can do about 1 billion times a second, 1 billion instructions a second. So you can kind of imagine what's going on when you're running a computer with this fetch execution lifecycle. And here's a little illustration that I took from an image on the internet that shows you this fetch execution cycle a little bit clearer. What's going down when you're interacting with the CPU and these instructions. What's happening is you're grabbing from RAM, and RAM, remember, contains programs data. You're grabbing data there for instructions, and you're constantly decoding the data, which is stored in registers in RAM, and then executing it on different parts of the CPU, either the control unit or the ALU. It's a loop, though. It just repeats over and over and over. And again, for CPUs nowadays, you get 1 billion times a second. So when we talk about C programs and writing C programs, at the very low level, underneath everything, we're just interacting with the CPU via our higher level programming language. So a higher level programming language. Higher level programming languages make it easier to write programs. Now, if we were to have to, again, understand all these instructions on the CPU, it'd be very difficult to write. And to understand all the instructions, that usually means it's an assembly language. If you've ever heard the term assembly language, it just means you're writing a program at a very low level where it's such a low level that you understand the instruction set. And you can imagine that if you were to write all of your programs with all these instructions, it would be very inefficient and very difficult to write a program. So higher level programming languages are the opposite of an assembly language. It's a much higher level. An example is C. C is a higher level programming language. It describes the actions that the program is going to perform in a much more abstract way. You don't have to memorize the instructions on the CPU. You just understand the language itself and you solve problems through these algorithms. It looks much more like the English language. It's much more easier to understand. If you were to look at an assembly language, what you're going to see is move commands with registers, with numbers, basically just numeric statements. And by using a higher level language like C, you don't have to worry about any of this. You don't have to worry about the instruction set. You don't have to worry about assembly language statements. So it's much more efficient and it's much easier to accomplish and solve problems. And so we're going to study C as our higher level programming languages, but other examples would be Java, Objective-C, things I mentioned. These are high-level programming languages that make your life a lot easier and are much more efficient. In addition to these higher-level programming languages, if you have this language that's more abstract, you have to be able to take that language and then run it on a CPU. You have to convert it, essentially, to instructions that the CPU understands. And so this is where a compiler comes into play. Often when you write code in programming, you're going to use a compiler that translates this high-level language, source code, into detailed machine language instructions, basically assembly language. So you're going to write a program that's going to do high-level, more abstract thinking, and then the compiler is going to generate all the millions of instructions that go to the CPU on the instruction set. So we're going to use a compiler in this class to do exactly this. We're going to write source code in a much high-level abstract form, and then we're going to run a program called a compiler to convert that code into something that the CPU understands. Nice, the other thing about compilers is they're also going to check whether or not your program has valid syntax. So when you write code, you have to follow the rules of the language. The rules of the language are essentially the syntax, whether or not you have a semicolon at the end of a statement, whether or not you use certain keywords. If you do these things incorrectly, you're not going to be able to run your program. So the compiler is going to find all of these errors, and it's going to tell you and report back to you and say, hey, you didn't write your code correctly. You have to fix them before we're going to actually convert this stuff to the instruction set on the CPU. So we're going to get familiar with compilers in a general sense, how to use them, how to understand what they're telling us. High-level languages are much easier to learn, much easier to program in than machine languages. That's the gist of this slide right now, is that by utilizing a language like C, it's going to be much more efficient and easier. When we write a program, we're going to actually perform multiple steps. And I found this illustration that really describes the steps in a really nice way. So I took this from a book. It's a basic set of steps when you write any kind of program. From the first step of defining the program objectives, understanding the requirements, to maintaining and modifying the program. So let's just walk through these steps real quick, and you're going to be finding that you're going to be doing this in this class. You're going to be, when you start to write a program, you're going to follow all of these steps. The first step is going to be to define the program objectives. This is where you're going to understand the requirements. You cannot start writing code unless you understand what you need to do. So you need to get a clear idea of what you want to accomplish in this step. After you understand the requirements, you're then going to start to design the code. When you design the code, this is how the code is going to meet the requirements. What's the user interface going to look like if it's required? How are you going to organize your program? Are you going to create different functions and try to create different algorithms and so forth? Then you're going to start implementing the code. This is where you actually write the code and put it into an editor in an integrated development environment. You translate the design to the syntax of the programming language, in this case C. Understand the rules of the C language. So you can use any text editor. We're going to actually use something called code blocks. You'll typically want to use something more than a text editor, something called an IDE, which we'll talk about. Once you're done writing the code, you have to compile it because it needs to convert it, the source code, to the low-level language. We talked about this already, so this is a pretty basic step. And then you run the program. Running the program is executing it, is using it. And then that's going to be the fifth step. After you run the program, you're not done, because even though you wrote the code and it may be meet the requirements of the language, it might not do what it's intended to do. So you have to test it, and you have to find and fix your errors. So just because a program is running doesn't mean it works. I get a lot of students to say, hey, it compiled, I'm done. No, you have to make sure that when you run it, it meets the requirements and it does what you think it's going to do. So you have to constantly test. And you'll be performing steps 1 through 6 over and over and over again. You're going to be finding that you're going to be writing code, testing, writing code, testing, writing code, testing. And typically when you do this, you want to do it in very small chunks. You want to write 2 lines of code, test, another 2 lines of code, test, and so forth. So you need to test and debug. Debugging is another concept. We'll have many lectures on debugging, but this is when you find and fix your programming errors. There are certain techniques you can do, certain tools you can use that help you find these errors. And you'll learn a ton by testing and debugging, because you always can learn a great amount of information by making mistakes. And that's going to be normal. You're going to compile, and the program's not going to do what you set it to. And you're going to learn from that. And that's what we're going to do in this class. I'm not just going to show you the correct way to do things. I'm going to show you the wrong way to do things, and then you're going to see why this is wrong. The last step is maintenance. This is when the programs are released and then used by many people, but still may have bugs. So for example, when Windows 10 is released, you'll notice that it still has bugs or still crashes. And so you're constantly getting updates. And when you get those updates, that's called maintaining the program. So just because you're done writing the code and releasing it to the public, it doesn't mean you're done maintaining it. Maintenance is often the most expensive phase, most expensive step, because when you release a program, it could be out there for 5 or 10 years. You're going to have to fix these bugs so that your customers are happy. You may also want to add new features to keep it up to date in the market. So maintenance is really important as well. Maintenance happens after you release the product to the customer. So for all of these steps, you may jump around, execute steps in different order, depending on what programming methodology. That's a whole other lecture as well. You're not always going to necessarily do these steps in a kind of waterfall approach where you start at the beginning and end at the last step. You may be designing and then going back and doing your testing and then going back and redesigning and so forth. So you're going to be jumping around, all depending on what's the most practical. From my experience, many new programmers in many of the classes in Udemy are ignoring steps 1 and 2 and going directly to writing the code. They're showing you how to write the code, but they're not showing you why you're writing the code. So this is a big mistake. When you start to write code, you need to understand the concepts. You need to understand the requirements. And you can get away with this in really tiny programs, but with larger programs, you're going to need to fully focus on design. Okay? So the larger and the more complex the program is, the more planning it requires. You should develop the habit of planning before coding. Do not just dive in. And you're going to notice from the lectures in this class that I do a lot of planning. I'm going to tell you in the challenges, when you start to write some code, that what you need to do and how you should design it. Right? Because this is going to make it easier for you to actually implement the code, which is step 3. So keep that in mind. You can often plan things by writing things down on paper. There's all sorts of nice documentation, designing languages out there and things you can use. But you always want to basically plan efficiently. And then as you're coding, I mentioned this earlier, but this is another very, very important concept. You always want to work in small steps, divide and conquer, and you want to constantly test. You do not want to write 100 lines of code and then say, oh, I'm done, let me go test. Right? Because now, if it doesn't work, there could be an error in any 100 lines of code. It's going to be much harder to solve that problem. But if you write code in little chunks, 5 lines of code, test it, then write another 5 lines of code, test it. It's going to be much easier to find and fix your errors. So let's focus on divide and conquer when we write our code in this class. I hope this helped. Again, this is just some basics. I wanted to provide some basic terminology. A lot of you may already know a lot of this information. But when you're learning a programming language, you have to understand these basics. Thank you.